So the last talk here before lunch is by our extremely active HamSCI member and working on WSPRDaemon that Robinette mentioned a little bit earlier, and is going for the in-person longest path competition winner. You and Chris Deacon came over the pond. So he's going to talk about some of the work I think he's been doing on WSPRDaemon, specifically, as it says up here, some changes of analysis and changes in propagation and also refraction height by the annular 14 October 2023 eclipse. So, Gwyn, I'm delighted to have you here, and the floor is yours.
Thank you, Phil. And I don't think I've ever in my career followed a talk that includes a pink pig. So that will stick with me forever. It's my great pleasure to attend HamSCI workshop in person for the first time in 5 years, and I'm very grateful to Nathaniel and his grants for supporting my participation. And I also acknowledge these individuals and organizations for the tools and the data collection that have enabled this study. No, it's not the down arrow.
Arrow, I believe. Let's try that one.
That one? No.
You just have to click here first, and then the arrow.
Two clicks. Click at the. Oh, should work now. Okay. So my motivation for this work was to test out the capabilities of Rob Robinette's WSPRDaemon software and the collective capability of the user community to extract maximum information from the WSJTX modes. WSPR metadata, so the existence of a path of known length between transmitter and receiver on a particular band at a particular time, has been used to study previous eclipses. But I wanted to look at the measurement capabilities of WSPR and its stablemate, FST4W, that could provide additional information. So specifically, using Rob's WSPRDaemon program, we can tease out not just the signal-to-noise ratio, but importantly, by measuring the noise, we can also have the signal level. And by using FST4W, we then get the spectral width as well. And we have Doppler shift with a 0.1 Hertz resolution. So what can we use those measurements for? And I'll show today how we've been able to look at reduced total absorption in propagated in noise and on one-hop paths, the effects of lowered F2 critical frequency on circuit reliability, and changes in propagation modes. We've heard of mode splitting earlier. And we also look at the anomaly in the height of refraction on a one-hop path using a WSPR sonde from Paul Elliott at 3 different frequencies. So let's start with reduced total absorption, and this results in an increase in propagated in noise. I have to say that in the USA, you are blessed with 2 wonderful locations, KPH and KFS, on the California coast, and also with the people that have installed very low noise receivers at those sites. It's a dedicated group. It's a wonderful resource that I draw your attention to. So what you see there is, on any day, so 3.5 megahertz, the noise level is high during the night when the band is open, and then it drops. This is D region and E region absorption happening every day. And look at that drop in noise level at this low noise site. Now, what happens during the eclipse day? So these are normal days, and this is the eclipse day at the start. Almost immediately there is a change of slope. The noise level stays high and until the maximum of the eclipse, and now it's 11 dB below that of nighttime noise, and then it falls away. And at the end of the eclipse, the noise level has returned to that of a normal day with normal D and E region absorption. If we look at 7 megahertz, the noise behavior is somewhat different. the noise level actually returns to the nighttime level. And that must be telling us something, and I need an ionospheric physicist to tell me exactly what it's telling us. There is a chasm between these simple observations of noise and known unknowns and physics. So the known unknowns are the spatial distribution of noise that propagates in to KPH and KFS. Now, using three-dimensional PyLab ray tracing, I can find the spot locations on the ground and the locations of the transients of the D layer where noise might be arriving at KPH and KFS. But actually, I fool myself because I have no idea of the noise contributions over the ocean, over the cities, over the countryside, over the desert, within that path of the eclipse. So I cannot make any progress. There is a chasm here. And there is a further chasm if I was to try and model the physics that goes on to affect that distribution of noise. So another aspect of reduced total absorption is that it results in an increase in signal level. Now, if we only had whisper, as on the left-hand plot, then we only have signal-to-noise ratio. And the dark magenta is the eclipse day. All of the light spots are on previous days. So what we see is that there is a change from the start to the maximum to the end of the eclipse in signal-to-noise ratio. But hold on. I've just shown you that noise changes. So what does SNR, signal-to-noise ratio, mean when the signal might change and the noise might change? So without WSPRDaemon, without the measurement of local noise, we have a compromised estimator in SNR. So we need to compute the signal level, shown here on this middle graph, and now in dark blue, we have the anomaly of the signal level on the eclipse day. And on the right-hand side, I compare the anomaly in signal-to-noise ratio, which is in red, and in blue is the anomaly of the signal level. And there's about a 10 dB difference between them in the medians. So very much SNR is a compromised estimator of the increase, the change due to reduced total absorption. So can I look at any of the physics of signal level variation and the obscuration factor of the eclipse? How much of the sun's area was covered and how that changed with time at the mid-path location here from Nevada to KPH, a 550-kilometer path on 3.5 megahertz. So what I have on the left-hand graph is in dark blue again, we have the signal level, the uncompromised estimator, and in light cyan is a normal day, the 15th of October. And the solid curve, I have fitted a very simple function that takes the obscuration factor of the eclipse with the cosine of the solar zenith angle that allows me to simply model the normal diurnal variation of absorption in the D layer. And there's a difference in response. There's a difference in response from the start of the eclipse to the maximum, where the fit isn't great, but actually from the peak of the eclipse to its end, I think you'll agree that those blue dots, the observations, track that very simple two-parameter model quite well. The right-hand graph, I take away the effect of the solar zenith angle, the diurnal variation of absorption, by taking the difference between the eclipse day and the 15th of October. But this introduces added noise because I'm taking away two measurements. But when I do that, I have a similar picture, that is poorer agreement between the start and the maximum of the eclipse than between the maximum and its end when looking at an effect of absorption. So now let's move on to an effect of lowered F2 layer critical frequency. And I'm going to do this on 28 megahertz on a 2-hop path from John TI4JWC, the red map pin in the lower right of the map in Costa Rica. And I'm going to look at 4 receivers, 2 in California, KPH and KFS, and ND7M and KA7OEI in Nevada and Utah, respectively. And the distance of KFS KPH is towards 5,000 kilometers and around 4,400 kilometers for Nevada and Utah. The top graph on the left is circuit reliability, and we see 2 dips, one at about 1630 and the other one at about 1710, 1720 at KPH and KFS, but they don't drop to 0. So the circuit reliability in 20-minute intervals stays above 20%. That's quite different at the sites that are closer to Costa Rica. There are distinct gaps. In fact, there are 2 distinct gaps where the signal returns for a short while. Now, what I think is happening is that the eclipse first affects the second hop from Costa Rica, the hop closest to California, Nevada, and Utah. It's affecting that. And then it recovers after it's transited that, and then it starts to affect the first hop from Costa Rica. So the hypothesis was that the critical frequency was reduced such that we pushed the Utah and Nevada receivers into the second skip zone. Now, using PyLab, so Python wrapper with PyLab, I can simulate this in a crude way in that I have to drop the sunspot number artificially to try and push ND7M here on the bottom graph and the Utah station out from being able to receive those signals on the top graph with the effective sunspot number of 125, but when I push the sunspot number down to 70, the Nevada and the Utah stations go into the second skip zone. They don't hear anything. That's like what we observed. But KFS and KPH still have rays going to them with a sunspot number of 70. So that's my estimate of the effect of the eclipse was equivalent to dropping the sunspot number from 125 down to 70. Now, there's another intriguing outcome that's come from that long path experiment. It looks at the eclipse path here in this map, but I've included Europe. So myself, G3ZIL, Southampton in the UK, my great circle path goes into the throat of the eclipse. And on 21 megahertz and above, the second and third hops, as shown by this PyLab simulation, will be in the path of the eclipse. So my experiment is, will I see a change, a dropout in my 21 or 24 megahertz signals across to the USA, North America, during the eclipse? So that's what I'm going to be looking for. And I've written a short news item for the RSGB in the UK, the Radcom magazine, to try and encourage other UK stations to work 21 megahertz and above on that day, and indeed either side. So let's have a look at some other effects. The lowered critical frequency actually changes the propagation modes. And we can study this using frequency spread measured by FST4W. So the cluster A on the left-hand side, the red dot is for the eclipse day, and the other colors are for other days, and the frequency spread in millihertz on the left-hand scale there is low. It's generally below 100 millihertz as the path first opens. It's pure one hop. But on this circuit, it's 1,808 kilometers, as the day progresses, it changes to a mix of one hop and two hop, and we have that mix of signals. But then on an eclipse day only, we have that cluster B. In the red dots show me that the frequency spread has now gone well below 100 millihertz. So the paths that were one and two hop mixed have become pure one hop as the critical frequency has dropped. Let's have another look. So we've seen that two hops can change to one hop because of the reduced critical frequency. So what happens if we've got a one hop signal that's fairly marginal? What happens to that as the critical frequency drop? It becomes two hop side scatter. Now, George Kavanagh gave a presentation earlier this morning, and what he really was showing was, I'd suggest, two hop side scatter. This is a 1,055 kilometer path from Washington State to KPH. On the top left there, we have in cyan signal level and in orange frequency spread, and the start, maximum, and end of the eclipse. Now, those points in the middle there, the cyan and the orange, may look like random data, noise, outliers, and you'd think, oh, what on earth's going on? Those points make eminent physical sense. But let's not look at them as a time series. Let's look at them as the graph on the bottom left, where we're doing a two-dimensional plot of signal level on the x-axis and frequency spread from FST4W on the y-axis. And then let's add some contours in there so we can see where the majority of the points lie. And you can see cluster A, most points lie in cluster A. It's very tight. This is a tight relationship of signal level and frequency spread. It's one hop. It's pure one hop. That's what we're going to have. Points B have lower amplitude and up to 30 dB lower amplitude. Where else have we heard that this morning? 30 dB lower amplitude. Two hop side scatter. And it's got much higher frequency spread. So as the one hop path is no longer supported by the critical frequency, what's happening is that the signals from Washington State are going off about 1,100, 1,200 kilometers out to the Utah desert. That's the arrow there. And they're being scattered back from the ground, back over a one-hop path to KPH. So two-hop side scatter. And that's a model there. And if you want to know more about two-hop side scatter, I've got a poster tomorrow. Now, cluster C only occurred to me at the airport. Cluster C is from the confluence of so-called high-angle and low-angle rays in a narrow band of about 40 kilometers just at the start of the region of propagation. But so I have a whole topic to look at. So what about anomalies in height of refraction? We've seen Doppler measurements this morning. The WSPR sonde can measure the Doppler shift. On this upper left-hand graph, we have three frequencies, starting with 3.5 megahertz, 7.04 and 10.14, the WSPR bands. Now, 3.5 megahertz on this path was open all night, so we see the diurnal change in Doppler shift, and then the 80-meter signal goes to being refracted by the E layer, which isn't moving. We don't see a Doppler. It becomes a flat line. But now you'll have seen that 7 megahertz opens in orange with a higher Doppler shift. It's a higher frequency. And then, in turn, 10 megahertz opens, the cyan frequency. Now, when we put those together and convert to path length, then they collapse onto one graph on the bottom left, except for 80 meters when it's switched to refraction from the E layer. Path velocity to height is some geometry, but what we need to convert to height is a single seed value. It's the constant of the integral. And I get that from the ionosonde at Point Arguello, California. So we have on this rather busy graph the Doppler shift converted to path length, converted to height change relative to that dashed line at 1500, which is the height from the Point Arguello ionosonde. The green trace, the one that's very smooth down below, that's the 15th of October, a normal non-eclipse day. And we've seen earlier that there is the anomaly in Doppler, hence path length, hence height of the ionosphere on the eclipse day. In magenta, the solid line is that from the Grape receiver at St. George, Utah, and the cyan dots from the WSPR sonde from Paul Elliott at 10.14 megahertz, the orange at 7.04 megahertz, and we just see at the start of it until it goes to E, the dark color from 3.5 megahertz. So those estimates, they're pretty reasonable. There's good agreement. And the anomaly in height of refraction from a normal day between the Grape in the magenta curve and the WSPR sonde on the red dots is around 30 kilometers. There's only 1.5 kilometers difference between those two instruments. I was most pleased when that came out. But look at the graph below. That's the change in height from the Point Arguello ionosonde. It has data dropouts. I've got no idea really as to when the peak was from that. So these measurements that the amateur community is making is in fact more useful than the immediate data from that ionosonde. And so to conclude, that's a map of the WSPRDaemon receivers and transmitters that were within at least the 60% obscuration for the eclipse. All of the extended data, of which I've only shown you a tiny fraction today, it's all in the public domain. The extended information from Rob Robinett's WSPRDaemon database on noise, signal levels, frequency spread, and Doppler, it's a rich data set. It's a high-quality data set, and it adds considerably to the metadata from these digital modes. We've seen the eclipse-induced changes to noise and signal levels. They're straightforward to observe. They're far more difficult. I'm looking at my scientist colleagues here now. The challenge to them is how on earth do we get from the observations that I, as an amateur, can make to some physics. And while PILAP ray tracing is useful, a dynamic ionosphere model, I think, is needed to simulate these transient features. Thank you.
That was terrific. Where did the microphone went back there. Okay, we probably have time for a question or two. There's a lot to unpack in this particular presentation. Does anyone have one? There's a roving microphone right there. Okay, so I'm going to ask a question because I'm standing up here. Can you go back a little bit? You had, so I was remarking on the asymmetry that you saw between the approach to maximum and the retreat from maximum, like there.
Yep.
The orange curve to the blue curve on the right-hand side there, you notice there's this asymmetry. We have seen this sort of different asymmetric behavior in other eclipse measurements using different systems like radars. I wonder how, you're showing, of course, this one graph. Are there also asymmetric measurements like that in the other data that you haven't been showing?
Oh, I think you're sending me off to do some more work, aren't you, Phil? Yeah.
Yeah,
That's always good. Yep, that's for the next grant proposal.
Beautiful. Because it turns out that the ionospheric response is not symmetric because things cooling down and things heating up don't necessarily go at different rates, especially when the density has changed after coming into an eclipse and going out of it. And I would agree with you that the modeling, more sophisticated modeling, IRI is a climatological model, which is underneath a lot of the refraction. There's more work to be done in there to match what you're observing. So that's what I would encourage. If you can come up with an ensemble of measurements that also show that, that's very attractive to aim at for modeling.
Right. Thank you.
Great. Other comments? Questions? All right. Thank you, Gwyn, again. That was really excellent.